Okay, so this is my first live shot of the semester here. It's pretty good. I just did this one back a few minutes ago. I did the 10 o'clock in the Zoom lecture slot. I did this already. So we're ready to go here. We're ready to go. All right, I'm pulling up my slides. I'd give you the Darden version of the midterm exam review, and see what you think. So here is the truth of the matter, what's happening behind the scenes for everyone, right? So on the left is obviously your side. Sounds like, got an exam to take tomorrow. On the right is our side. Got an exam to give tomorrow. And that, of course, I know gives you zero comfort right now, but it is true. And the good news is, after you get started, it will be over shortly after that, win, lose, or draw. So we'll talk about some things that help you do well, and we'll talk about some of the things that are going to be on the exam, and hopefully we can take some heart from this. So I'm not trying to get your sympathy in how hard it is for me to give this exam to you, but do know that for you, regardless, it's going to be over in an hour and 40 minutes, or 2 hours and 20 minutes after you start. So that's one thing you can take from it. Time is, of course, important on this slide, and location in these COVID times is wherever the hell you're locked up right now. So you got that part figured out. The when is, of course, starting tomorrow. There's 3 different slots for people all around the world. We've got a 9 a.m., a 6:30 p.m., and then an 11 p.m. Those are all Ann Arbor time locally here. Make your own adjustments there. The one on the bottom that says Thursday has to do with the fact that at 1:20 a.m. it is actually Thursday. It still starts at 11 p.m. on Wednesday, Ann Arbor time. You got 140 minutes in each one of those slots. That's 2 hours and 20 minutes. This is going to be done online. I left my water somewhere. It's going to be done online through Canvas and Gradescope. So the Canvas is going to be like a Canvas quiz. It's a multiple choice thing. You go ahead and fill out some multiple choice questions there. And then the written part is, exactly, barely even feel it. The written part is going to be on Gradescope, just like our lab stuffs are done. So that should be straightforward. You should have already had practice in all of the formats of this exam. One thing that's important is the question for the Gradescope stuff, the questions for the Gradescope stuff are at the end of the Canvas quiz. So you don't want to finish all your multiple choice questions and then hit submit, because you won't have access then to the questions you need for 25 and 26. All right, I found it. There's also an honor pledge, which is a separate Canvas quiz. You have to fill that out to, state your honor pledgey stuff. Didn't cheat. Don't know of anybody that cheated. Good thing. Let's be honorable. The entire exam is not on one page. You will be scrolling through whatever you've got on the Canvas side, and then you'll have the separate problems that you do in 2 separate files for the Gradescope stuff. During the exam, we can use the Piazza for questions. This is be like, heading out to the hall to get some clarification. We're going to set everything on Piazza to private, so you can post there. No one else will see it but us, and we'll have an army of staff members just waiting with bated breath to see that first. We have them answered in seconds here. But don't use that time to wait, right? So if you do come up with a question that you feel like you need some clarification on, go to Piazza, ask the question there, and move on. Because any time you spent waiting is time you're not scoring. We're trying to get you to get as many points as possible, and leaving those points on the floor is bad. Putting those points on the board is good. So if you have a question, post it on Piazza. Someone will get to that. The other thing that's important is, because this is a randomized exam, if you say I'm having a problem with question number 12, I will probably have no idea what your problem is. So if it's something that needs clarification, do take a quick screenshot, post that up there with your private post. Everything is set to private by default. If it turns up as a public post, it's a big no-no, and it was probably something that you purposefully did to make that public. Don't let that be you. So post it up there and then move on. Like I said, you can come back and get to that answer later. Another thing that's important, don't shrink your Canvas browser. If you zoom in so far, the pictures will disappear. And I know it's a weird side effect of the way that they do the graphics and the quizzes. So we had a couple of exams here in the last few semesters before we figured out what the problem was. People are making their browser too small, and then Canvas just, I don't know, the size of the pictures are unnecessary. So you will miss some images. Excuse me. You'll miss some images if you make it too small. The policies are, of course, the things that have been with us throughout 281 so far. Anything that we have given you, feel free to use. This is lecture PDFs, stuff from lab, anything that we've given you, feel free to use. During a normal semester, we have people use a cheat sheet because you're in a room with us, and there's an 8.5 sheet of paper, 8.5 by 11 sheet of paper. You can use one side of it. We're going to get started with how to win at testing here, because I want you to win on this one. So one of the things that I say is it's a good idea to make this cheat sheet even though you don't have to use it in this particular situation here. You're still bound by the same rules. You're supposed to be using what you know and what you can fit on one sheet of paper. So we would like for that to be done. But the other thing that's important about taking the time to write this stuff down is as you study, the more you study and the more you write this cheat sheet, a really, really well-written cheat sheet is almost never used because the work that's gone into making that thing focuses you so much that you find the things that you need to know, find the things that you don't know, you get that covered, you write down as little as you need to, as much as you want to, and then you've got everything there at your fingertips. So it's good because I said you can use the lecture PDFs, but there's probably about 500 slides that we've gone through. If you need to find something and there's 500 slides you need to search, you don't have that much time. Okay, we'll talk about time in a little bit, but if you don't have it at your fingertips, you're risking scoring. So having a cheat sheet done is a really good thing. As well, it says writing by hand improves long-term memory, which is also very important because the thing is when I start copying and pasting things into my cheat sheet, then I've got more information than I need. And I end up doing a secondary search. I know it's on here somewhere. I just made this cheat sheet yesterday. It's got everything I might possibly need, but no, I just made it yesterday, so I don't remember where everything is. When you write it down, you write the minimum amount of information that you need, and you know exactly where you put it. And that brain motor cortex that helps you make the loops and circles and lines and dashes while you're writing with your actual hand, it does something else in your mind while you're studying that helps you with memory in a way that just typing doesn't, in a way that just copying and pasting does not. So if you want to do this, I would strongly suggest you write this. I learned this the hard way in college. I was taking notes, to take notes all the time, and then I realized at one point, I'm like, I take all these notes, and I never read them. That's kind of stupid, because I just didn't study. I just took the notes, I went to class, I just didn't study them in notes. I never really mastered that skill. So then I decided, well, I'll just stop writing these notes down. It's just a waste of time, and it's making my room a mess, because I just bring them in and I throw them on the desk, throw them on the floor, they're everywhere. I stopped taking notes, and I started doing worse. Started taking notes again, still not reading them, and I started doing better again. And because this motor cortex thing helps. And the studies have shown that people sitting in meetings, even if they're just drawing hearts and flowers and loops and I love him and he loves me, if I'm writing those things down, those people do better on remembering what happened in the meeting than people who are just sitting there and quote unquote paying attention. So that is a skill that you can use. So write these things down, it does help, and then when you've got it all in one place and you know exactly where it is, you can get to it quick. There's some things you're definitely going to need on there. You're definitely going to need the master theorem. To this day, I don't remember the master theorem. I look it up when I need it. It's a good thing. Other things you might put on there, a simple chart that says this sort is stable, this sort is worst case this, best case that, sort of things like that. So you can use those notes on the exam, put it in there. That's the way that you should be doing it. The engineering honor code, of course, applies. So we're not looking for people to give us information that they don't know or things that they can't figure out on their own. This is an assessment of you. The multiple choice portion here, 24 questions, 2.5 points each. Total that up, there's 60 points of your exam. Each one of these things is a multiple choice. It's got 4 to 5 correct answers, so there's no true falsies on there. You're going to have to take a 1 out of 4 or 1 out of 5 to get the right answer. There's no deduction for getting the wrong answer beyond not scoring. So we're saying we don't take points away when you get a wrong answer. We just don't give them because you didn't have the right answer. So make sure that you always have an answer for all 24 of them. Even if you run out of time at the very end, throw some guesses in there. At the worst, you got a 1 in 5 chance to getting some additional points. So make sure that you always answer that. And here it says 1 answer per question because when we were filling things out on paper, people would often do multiple bubbles because they couldn't make a decision. That just guarantees you get it wrong. When we're going to be doing this online, though, I think you're absolutely physically limited to just 1 question or 1 answer. So that's not as important here. But know that as you're trying to figure this out, even if it looks like there might be 2 of them that are correct, 1 of them is not correct, or 1 of them is much more correct than the other one. So we're looking for the most correct answer there. So, and there's not a whole lot of ambiguity where there's multiple correct answers and 1 more correct answer. That's not the way that we try to roll in 281. So the exam itself, of course, I said all the questions are in the Canvas quiz. Multiple choice will be answered in the quiz just like labs. The writtens are just like lab written problems on Gradescope. But in the big bold letters here it says, do not submit, this is in presidential shout tweeting, do not submit the quiz until you are done with both parts, minus, the bad spelling. Because at the bottom of the Canvas quiz is where you can find the written stuff, the actual problems. So you'll need that there. Once you submit, if you submit it into Canvas, then you can't see the questions anymore, and it's a lot harder to do your Gradescope stuff. And then you're trying to get us to rescue you, though. So make sure you don't submit it until you're done with both parts. It doesn't mean that you have to do the multiple choice questions first. You can do them whatever order you want to do them in. Just make sure that you have it all done before you submit anything, because that will shut you down one way or the other. Here's a Canvas idiosyncrasy, let's call it. The exam time has a time limit, and in order for us to work this, we have some students that have accommodations and they need additional time, or some things that we don't have to really supply anymore, like to give you a quiet testing environment. That's on you to find out now. But as we make these accommodations, we've often had additional time, and so in order for that to work, we have to tell Canvas that all of the exams have that additional time. And so in the most involved ones, there's like a 2 times time, so it could be 4 hours and 20 minutes. So that's the size of all 3 of those exam slots, even though unless you have an accommodation, you only have those 140 minutes. So be aware that the time limit thing might say that you started late, but that's because you're not getting those 4 hours. You're still only going to get your 140 minutes from start to end. So you will get those. Pay no attention to that time limit thing or that started late thing. You should get those 140 minutes if you get there and start at your start time, even though it might look weird because Canvas is not that flexible. What to study? We've got the practice exam posted on Canvas. So far, I hope you've already worked your way through that mostly. The answers to that will be posted in about 75 minutes. So as soon as I get wrapped up here at 1:30, those go live. You can check those out. The accommodations people don't start early. They start at the same time and then they go longer. So they start at 9 and they've got the extra 50%, they've got an extra hour, so they got 3 hours and 20 minutes, or they got the 2 times, they got 4 hours and 20 minutes. Because the way we've structured the exam was originally a 90-minute exam. And we had the exact same structure for the final exam, and that was in a final exam slot, which was 2 hours. And so about 2 years ago, I was like, why do we do this 90 minutes for the midterm and 2 hours for the final when it's basically the same work? We could take some pressure off of them if we gave them 2 hours for the midterm and 2 hours for the final. So that's what we did. We went to a 2-hour exam, didn't add any more questions or change the format at all. So it's essentially written as a 90-minute exam. Now it's in 2 hours. Then COVID happens. We go inside and everybody's got to take these exams online. Some people have faster connections. Some people have spotty connections. Some people might want to print this out so they actually have a paper copy. So we gave you an additional 20 minutes. So that's why it's an hour and 40. It's because it's a 90-minute exam. An extra 30 minutes just to make things even and fair versus the final, and then an extra 20 minutes just to make things even and fair versus the internet and the world and time delays and all those things. So I'm saying that to set you at ease. It's very important. If we look at our first slide there, where it was like the student pulling out their hair because they got an exam, that is not the way I want you to go into this exam. I want you to go into this exam relaxed. I want you to go into this exam calm, cool and collected, because all that extra stress that you bring into it will not score points for you. So come in calm. I'm telling you about this extra 50 minutes. That's almost an hour extra that students who were taking this exam 3 years ago didn't have. You've got it now. Relax. When you're relaxed, your mind works better. So be calm, be cool, be collected. Make sure that you get yourself to a place where it's going to go well for you. All right? Physically, mentally, all of the things. At 1:30, those exam answers are going to come out. You can then double check anything that you've done on the practice exam. If you still have any lingering questions, take to Piazza, take to Discord, throw some questions up there. Somebody should get you an answer pretty quickly. They should be pretty straightforward though. Hopefully we can get that resolved for you. Of course, you can check lecture slides and recordings, in-class and lab exercises and materials. This is all stuff that you can put into how do you get better at this exam. Looking at projects, of course, there's not going to be a whole lot from the projects on the exam. For one, there's not going to be any pairing heap on there. Not a single question is a pairing heap question. Okay, applause now. No pairing heap questions, and not a whole lot from the projects in terms of how things are actually done, but we do expect you to know the fundamental coding stuff that you needed to use on the projects if you're going to be writing code for the free response questions. So in that sense, you don't have to study the projects beyond understanding how to use a priority queue. There will be questions in there about priority queues, whether it's their implementation or their usage or applying them to some problem solving thing. You can imagine there's going to be some priority queue stuff there, but there's not a whole lot in terms of like you need to go back and study your projects. And there's not going to be anything on there about get opt or things like that. The way that we work this is we take each one of the lectures in the first half from beginning up to strings and sequences, and we give each one of those lectures to a different staff member and say, write 4 questions about this, 4 multiple choice questions. Then we bring all the questions in, we edit them, we throw a bunch away, we make some easier, we make some harder, we make some clearer, we throw away stuff that might be too long to read or not worth it in terms of it's going to be much more work to get these 2.5 points. So we try to make this as nice and even as possible, and then we just put those questions into the pool and you start taking those questions. So that's how this is going to work in terms of what the content is going to be. It's going to be the stuff from those lectures. There's not going to be a question on pairing heap. There's not going to be a question on a project, right? So that's how it works. If you've got a study group, that's a great thing to have. Work with them. Pull one together this evening on Discord. Let's put some questions out there and figure that out. I got a challenge for you later, and I'll drop that in a few slides or so. Maybe you can make something happen there. One very good example of that is Andrew Zhu, our IA, was the master of this when he was in the class. So maybe you can hit that one like he did. So topics, I said we're covering everything here from complexity analysis, that's basically lecture 2, all the way down to strings and sequences. So in terms of that, what we're trying to get at is the content that we've covered. Now, I had a student just about a semester ago, maybe I guess it's since we're last on campus, said it's kind of like the midterm exam is like 203 and the final exam is like 280. Yeah, that's kind of a fair approach there. Just because the stuff in the first half is so much more theoretical, right? Complexity analysis is not really code, it's like theoretical stuff. And so we're not going to be doing the proofy things that 203 does, but in terms of what we do in the second half, when we're actually working more with these algorithms, there's much more concrete stuff going on, like the programming in 280. Whereas when we're working on the data structure side and understanding those things in the front half, that's where complexity analysis in the 203 field comes from. So that was a student's point of view, and I thought it was pretty apt. But in terms of these complexity analysis questions, complexity analysis is really one of the hardest topics to write questions about. Once again, I'm asking for your pity on how hard it is for me to make this test for you. But a complexity analysis question has to be very clear or someone won't understand what you're doing. And so the challenge in writing a complexity analysis question is making it clear enough so that people don't flood the hall to ask, what did you mean by this? but not giving away the answer. So as you look at complexity analysis questions, note that they might be a little tricky. They may even seem like they're a trick question. They really aren't. The only goal is to see if we can ask a question clear enough that you can actually answer only if you understand what's going on there. So that's what's there. Of course, recurrences are also a little painful as we try to get those figured out, try to get our recurrence relations. But knowing how to do that is important. Contiguous versus connected is of course going to be on there in terms of how you may have to implement something. Stacks, queues, priority queues, definitely things are going to be on there. Binary heaps, not pairing, and heap sort. So a heap is a pretty important thing in the first half here. We'll also look at the other sorts, the elementary sorts, quick sort, and merge sort. And finally, strings and sequences, which we covered about a week ago. And since I know that there's one question from the pool in that, there's only one question you're going to have on strings and sequences. And it's not that heavy a lift. So make sure you check that stuff out. You should be able to get there. How about answering coding questions? This is just covering how this is going to be done. If you decide you want a helper function, then you have to write it above the given function. And that's okay. If you needed a helper function to get this done, then we did too. So it gets figured into the budget. So you can't think of anything that you have to do on this that we haven't had to do as well. So as I said, the things that are going on in this exam are the same things that have gone on throughout 281. And generally our approach is we're going to give you a 50%, 150% budget. So if it takes our P1 solution this much time, you've got this much time plus 50%. When we're writing coding questions on the exam, if we give you a 24-line budget, that means we've got multiple solutions from the staff that took us 16 lines or fewer. Maybe the longest one was 16 lines, so we take that, multiply by 150, and say you've got 24. So if you see something that says it's got a 15-line budget, know that we got it done in 9 or 10. So that's what's going on there. So if you say, well, if I have to write this helper function, then they had to write a helper function. Or if you had to write a structure, then they had to write a structure. So if you need it and you can't figure out any other way to do it, then we did too, just like the rest of 281. So if you need to write a structure, you can write it inside the function or above it if you want. In any case, it's going to be something that's only used inside that function. So you could write it inside the function or out. It doesn't matter. Some of them can only be solved if you've got a struct or a pair or tuples if you want to get that deep into it. But if you need to do something with structuring data, then feel free to do it. You've got room for it, whether it's structuring data or making helper functions. If you need it, you can do it. In terms of counting these things, I talked about the line budget. So let's look at how we count lines. This first one, if x is greater than 0, result equals 0. That's an inline if, right? That really is 2 lines of code. It's the if followed by the body. In this case, since it's a 1 line, you can put it all in line. But even if you write it like that first version, we're going to count it like the second version. That's 2 lines of code. So don't worry about trying to save that space vertically. Visually, it's not, it may save the space, but in terms of the total count, it's not going to save you count. Now this one has got a bit longer body on the if, so I've got a curly brace to open it up and I've got a curly brace to close it. We think of this as 3 lines of code. That curly brace on the if, that's not really code. So that one doesn't count. We end up with just 3 lines of code here, the if, the assignment, and the return. So that's how that's going to go. If I look at this statement, this is an if and an else. The else counts as a line of code. It does. So this is 4 lines. If x is greater than 0, that's 4. However, down at the bottom, you see this exact same code written with the ternary operator, and I can get that done in 1 line. So there you see I can use the ternary operator, or I can use this 4-line if-else statement in this particular application. So save the space, right? Write it in 1 line. Our solution, however, was probably not written with the ternary operator. It was probably written pretty straightforwardly with the if then else. So note that if you're needing to use this ternary operator everywhere to get under the line budget, you might be missing something else in terms of your approach. Here's another one. If you had to do something with a struct or with a pair in there, here is an example from the word count demo that's coming up next week. If you've got a string and an integer in this small struct here. Maybe you needed to define that to use it for whatever's going on in your problem. You can see that I've got the ability to declare a vector of word counts there in VWC. And then when I want to push one back, you see that I've done an anonymous construction of one with curly braces. So I can say, let's make one of these word counts by just curly brace, string, comma, integer, curly brace. And what this does is it saves me from having to say, you know, word count W, W.word equals ABC, W.count equals 1, push back W, right? That turns that into 3 additional lines of code that you really don't want to spend. So this anonymous construction is the way to go if you're going to use structs or pairs or whatnot. In terms of the libraries that you can use while we're working coding questions, each question is going to tell you exactly what you can and can't do. It'll tell you what number of lines you can use, it'll tell you what time complexity or memory complexity you can use, and it will also tell you what is legal to use from C, C++, STL, and so on. So it might say you can only use vectors, or you can't use anything from the STL, or anything from the STL containers or functions are available to you. So it'll tell you very clearly what you can and can't do in terms of all of the things that are important. Complexity, space, lines, libraries. The function header that we give you is obviously going to set you up for what you need to be doing, and we won't count that line of code against you. We're giving that to you free, but you have to pay for the return statement if there's one in there. So any other thing that you add counts, but as I mentioned, if you absolutely can't get by without it, pretty good chance we didn't get by without it either. So that factors that additional line count into the solution because we spent it as well. All right, so this slide here is setting us up to go into talking about exam content. But I'm going to pause here to really get you ready for this exam. All right, this is my favorite part of talking probably in this course. I went to MIT. I was pretty smart. But I say that not to, I don't know, raise my profile. I went to MIT. Like, people there are insanely smart. So if you go to MIT and you're pretty smart, turns out you're pretty average. I was right there in the middle. I wasn't a superstar at MIT. I got it done. But I was really good at taking tests. So we're going to talk about some things to make you better at taking tests. Because right now, you got one coming up in front of you. And then for the rest of your career, you're going to be taking tests as you need to. So let's make this the beginning of the best test-taking part of your career. So test taking, as I mentioned, is about coming in and using your mind. You want to come in calm. People have physical routines. Maybe you go for a run before and you have a banana to help with the electrolytes and the potassium to get your recall up a half an hour before. Something. Figure out what your best physical prep for the exam is. Make sure that you're well rested but not groggy. You're awake but not jittery and too caffeinated. So you want to go in calm, because when your mind is calm, you're going to do well. So that's one thing that's very important. The other thing that's very important, I forget what they call it in one of the things, we'll talk about it later, but you want to go into this knowing that you're going to do well. Because when you know you're going to do well, that's worth points right there. If you wonder how bad this is going to be, how bad am I going to do, that's worth points too, but they're not worth points for you. So go in knowing that you're going to dominate this exam, and no matter what, 140 or 300 minutes from now or whatever it is, it's going to be over. I don't have to worry before that. I don't have to worry during, I worry before that as I'm getting ready. But during that, I don't want to worry at all. Any time that I spend worrying is not time that I'm spent problem solving. That's not time that I spent putting points on the board, because we really want to score here. We want you to score these points. So as you look at scoring points on this exam, another thing that's very important is to go into this like any professional. You're a professional now. You're a professional student. I know you've heard that before, and most of the time you just think, oh yeah, that's what I do. But think about how professionals do things. How do professional musicians succeed. They practice, they are prepared, they are ready to go, and they get it done. How do professional football players or basketball players succeed? They go in knowing how they're going to score points and knowing how they're going to protect themselves. You look at most football teams, they go into a football game having practiced the week, knowing the first 10 plays they're going to run come hell or high water. They're going to run those plays, and then we'll start making adjustments after that. I want you to translate that into how are you going to work this exam? How are you going to put points up on the board? We've already given you a whole lot of information. So there's 24 multiple choice questions. Each one of those is 2.5 points. So right away, you can say, well, how many minutes out of 140 is 2.5 points worth? If I spend more than that, I'm absolutely taking points off the board for me. Because if I spend 10 minutes on one multiple choice question, that's 1/14 of my time, and it's not 1/14 of my points. So go at this like someone would say, what happens at halftime of the basketball game? Well, coach comes in, makes some adjustments. We might change our original approach. We've seen what they've got, and then we're going to come back with something new to make that happen. How do we translate that to the exam? Primary thing you want to do in an exam, read every question first. From start to beginning, from start to end, read those questions. I know you want to get those points on the board. You're thinking, oh, I can answer that one right now. Let's do it. I want to get those points now. Read them all. Here's 3 reasons. First reason, probably the most important thing. Your number one aid on this exam is going to be your brain. When you can put your brain to work on these problems, that's when you get points. I realized in college that I was being able to solve problems while I was asleep. I would work and work and work and work. Maybe I didn't get it, but then I had to at some point go to bed. So I would go to bed with a calculator, pencil, and a stack of paper next to my bed, because very often I would wake up in the middle of the night, roll over, write something down, plug it into the calculator, oh yeah, that's right, and then go right back to sleep. Get up in the morning and then be able to use that going forward, because while I was asleep, my mind was working. How do we translate this to the exam? You read the exam first. Now you've got 26 problems in your brain. They're all being worked on by your brain. Even though you personally may only be focusing on one of them at a time, your entire brain is able to work on the entire exam. So that's one that you can get yourself going forward. Another thing that's very important about reading the exam, right? I like to call this one the oh shit factor, right? If you've got this exam coming up, you read one problem, you're like, oh, that's hard. Then you get done, you're like, oh shit, now I got to read another one. Boom, and then that's like, so you end up with these 26 different shocks throughout the exam, because now it's a new oh shit, and those are evenly spread out through the 140 minutes, and that keeps your anxiety level up here, which means your scores are going to go down there, right? So you read it all, you get 26 oh shits in a row, and then you got 135 minutes to just bust it out. You know that question's coming. It's not any scarier than it's going to be. You might not know the answer any more than you did before you read it, but it's not like another surprise. It's like somebody keeps kicking the back of my chair is what that is, right? I want to get all the kicks out of the way, and then I can go at that, right? So that's really important for that. Make sure that you get this read, and as you're working on it, then you start to get to these answers. And then the other thing that's really important about this reading ahead of time is where we can move that halftime talk with the coach into our favor. So before the exam, I'm talking about the football team's game plan. You need a game plan. How am I going to get these points? Well, I think I'm going to do really good on these multiple choice questions. I'm always good at multiple choice questions. So maybe I'll spend a little less time there. Maybe I'll just spend 2 minutes per. That's 48 minutes, which leaves me now a full-on 102 minutes to go at the rest of these free response questions. So maybe that's what I think is going to happen. And so I write that down on the paper. Write that down on your cheat sheet. This is plan A. Plan A is 2 minutes per multiple choice question. Then I know that the last 2 questions, they're 40 points each. One's 16, the other's 24. So one of them's 50% more important than the other one. So maybe I take that and divide the remaining time up evenly, just like that. 40% for this, 60% for that. Make a plan, right? Make 2 plans, because maybe after you read it, you're like, oh yeah, I'm gonna crush that free response question. I totally get that one. Then that gives me more time to spend on my multiple choice questions to make sure I get more points out of there. So write up your game plans, maybe 2, 3, 4 of them. After you've read the exam, you say, oh, that one's definitely not gonna be the case. There's no way I'm gonna get all of these multiple choice questions with 75 seconds each, right? Okay, I've gotta have at least 2.5 minutes, and maybe I'll spend that 2 minutes on the first pass, and then I'll do the free response questions, and I come back and make sure that I've saved myself 30 seconds, another 12 minutes for each one of those 24 to make sure that I got it right. Or, you know, maybe 10 of them I know I got right, and there's 14 that need a little bit of extra work. And so now I give them a full extra minute instead of a half a minute. Going with a game plan because you're the coach, and then you've written these things down, and then you can say, well, I'm crossing this one out and crossing this one out because I know this exam is looking like it's going to go this way for me. And when you've got that on there, then you could be like, okay, I know at minute 16 I should still be working on multiple choice questions. At minute 47 I should have switched over to free response question number 1. Whatever it is, make a game plan. This is how professionals succeed. They have game plans. Whether it's in business or in music or in sports, if you don't come in with a plan, you know what they say, failure to plan. Plan and a fail. I don't want you to fail. I want you to score. I want you to score big. So come in and allow yourself this read. It feels terrible because you want to get on them points. But with that read, you can set your mind to work on all the problems. You can knock out all the oh shits. And you can also decide which strategy is going to be the one that gives me the most points. So that's how I want you to approach this exam. Like I said, this is how professionals win. This is how I ended up doing well. I came up with all of these strategies on my own, and then later on I realized as I put them together, this is how I did so well in school. So use this, and every time you've got another exam, pressure the instructor to say, what's the structure of the exam? Tell me how many questions are going to be. What can I expect out of this? And we're trying to do the best that we can by you in 281 by telling you as much as we can about it. I'm not giving you any answers, but we say there's 40 points here, 60 points there, 24 questions here, 2 questions there. Take that and use it, because when you use it and you say, I know I'm going into this, I'm going to come in relaxed, I'm going to read them ahead of time, knock out all of the scary stuff, and then I'm just going to focus, use my mind, use my skills, you know, go back and then do the other good test taking things. You know, if you're going to do a pass on this multiple choice question, you might look at one of the first distractors and be like, I know that's definitely not the answer. Cross that bugger out, right? Write down a list of questions that you have to revisit, and everything that you know about them, write that down too. So like when I come back to number 21, I remembered I already crossed out A and E. I don't even have to look at those. I just need to figure out which one B, C, or D is the one that I feel the most. So then in the end, if I end up having to guess, I'm not just picking A through E. I know that it's only one of these 3. So I've got to raise my percentage from 1 in, you know, a 20% chance to the 33% chance. Whatever it is that gets you more points is going to make you better at this. So as you work on these things, this is how you need to think about it. In terms of writing the free response questions, right, there we need you to be writing good code, essentially. But it doesn't actually have to compile. The auto grader isn't used on this the same way that we use it in project stuff. So if your code doesn't compile, not the end of the world, right? I've seen problems, I've seen solutions that didn't even get exactly the right answer that are still worth full credit, because the way we do this is we break the problem up into things that we're looking to see. This is something you should appreciate as a 281 student. I say that there is a linear number of ways that you can write one of these things wrong. Meaning that every single one of you might come up with some whack idea and write it wrong. So in terms of a rubric item, I'm not going to try to write things that I can take away. So I might not think of that as a way to write it. So why would I write a negative for that? But what I am looking for is you to find that positive way to do it, because there is 1 or 2 ways that I really want you to do this. And so there's a constant number of ways to do this right, and there's a linear number of ways to do this wrong. So we structure our rubrics accordingly. We say we're going to give points when somebody does something right. That's it. It's real simple. So you're trying to get those elements on there. And sometimes you can break that up. It doesn't have to compile. It has to have those elements. So, you know, a complicated DP problem in the second half, and you maybe not even figured it out, but you realize that at the end I'm going to have some table, and it's going to be the smallest value in the last row. I can write that find min at the very beginning. And that's oftentimes how I end up grading it. I'll go look for the return value. Oh, they got that. That one was easy. I look for setting up the variables at the top. They got that. That's easy. It's a lot harder to grade the body of the problem. So you're just trying to get elements in there. So if it doesn't quite compile, not the end of the world. What's important about that is don't spend time getting it to compile. If you can't and you think you know what's going on there, get that stuff down there. Get it all written, right? If you need to write some comments in there, be judicious about commenting. There's a good reason to write comments, and that's for maintaining code. Comments are great for that. It's also good for clarification, because I would say, you know, higher than 9 out of 10 people who can't explain a solution also can't write a solution. So if you can comment it out, then that's one way to say I know how to write this solution, right? At least I understand it. Getting it written, that's a separate step. So don't worry about putting comments in there, because you're not trying to maintain this code, right? And the only reason you might need a comment there is maybe to clarify something. For instance, you got a brain block going on. You can't remember pushback is how you append things to a vector. You're like, but I'm just going to write append as a function. It's not really a function. I'm going to write it. And then maybe a comment, I can't remember the name of this here, right? What's going to happen there is you'll probably get full credit if what I needed you to do was put the thing on the back. And then I'll write you a 1 or 2 point syntax deduction because you didn't actually get the function name right. So if you need that comment there to clarify something, do, but don't waste a lot of time. As I talked about it, these things are fairly simple in budget, like 16 lines, 20 lines. I think I've seen a 30-line problem at some point in the past, meaning that there was only 20 lines of code to write in the first place. How much time do you have to spend writing comments when, you know, a 15-line budget was really because somebody on staff did it in 8 or 9? You could have written it in 8 lines or 12 lines. If you spend time writing 6 lines of comments, I mean, you should be writing code, because you can't guess at code. You can guess at bubbles, right? When you get down to the end of it, you can't guess 6 lines of code onto your program. You can guess probably 3 bubbles in 5 or 6 seconds, right? Especially with not having a bubble and just clicking on boxes here. So keep that in mind as you're trying to budget your time and try to score your points, trying to say, where am I going to get my points from? How am I going to budget these things? And what's going to be most effective for me? So writing comments, if it's effective in the sense that it allows you to set up what you're going to write with actual lines, set it up so you don't make mistakes, and then fill in the actual code. But we're not looking for style. We're not looking for comments for much of anything. I mean, if there's some really weird situation, we're trying to find a way to give you points. Like, I just don't know if she understood what she was trying to do here, or if she got some syntax wrong, or if he forgot and renamed a variable here by accident. A comment there may help you, but for the most part, comments are not going to help you. So don't spend a lot of time in them, only if you're like completely befuddled. You know, if you say, well, I know that this has to be less than that and this has to be greater than the other thing, you know, that could be worth you getting 2 points if you're at a total blank on a question. You're like, you're not going to pull anything in there. I might find a way to give you 2 to 3 or 4 or 5 points if you've got something there, but you're certainly not going to be getting the lion's share of anything by writing pseudocode or writing comments. We want real code. All right. Yes, I know I said wacky ideas. I wasn't talking about you in particular. Keep that in mind, whoever you are. All of you. I wasn't talking about that. I was talking about all the other students from previous semesters that have wacky ideas. I know that now that you're here, you're going to make this happen solid. I'm really counting on you. All right? So, take a plan into this exam. Do what I just did. Take a breath in this exam. You've got time. Make sure that your body is good. Make sure your mind is good. Go in confident, supremely confident. Go in prepared. And if any of those things are missing, you're still going to be done in 140 minutes. Even if you don't have the best place to sit, or if you're a little tired, you got to grind it out. If you didn't get that cheat sheet written, you know what? You're still going to do very well. You're here with me now. You've been here with us all semester. I know you're pushing to make this happen. There's crazy times, but you're working hard at this. I think you're going to succeed, and you're going to put these points on the board. I'm looking for a really high average on this exam because you did it. All right? Oh, This is a slide that we've already seen before here. This complexity analysis slide. This is something that you should just understand, right? When we ask questions, if it's a complexity analysis question like this, we may have 4 or 5 options in the question, in the answer options, but they're going to be in order like this. Like, you know, first constant, then logarithmic, then linear, and so on. So what that allows you to do is say, in a very physical way, is like, oh, I know it's got to be faster than n log n. So that allows me to rule out D and E. So now I just have to figure out the 3 things that are faster than that, A, B, and C. I have to pick between them. So they will be in order, and that's helpful. So just, I know that you understand this. This is just here to make sure you sort of grok it. That's a really old term. Just understanding what complexity analysis means here, and keeping those complexities in your mind so that you can sort them in a way. So here's a couple of really simple ones, also previously seen code here. We know that as we're trying to figure out how complexity gets counted, the important thing is what? The loops. So here in this first bit of code, I've got a loop that goes from 2 to 7 and then just a constant amount of work there in line 8. So it's only the loop that matters here, and we see that as binary search, so we know that it's going to be. But in situations where I don't know what it's going to be, how do I figure out what this means, right? So I see that the while loop is controlled by high versus low. So as long as high is greater than or equal to low, I stay in. And then what I need to know is how do high and low change throughout the rest of the slide, or the rest of the code, right? I see that load gets adjusted to something near mid, or high gets adjusted to something near mid. And what is mid? Mid takes the entire range and divides it by 2. So I see that division by 2 there in line 3. And right away, even from like 400 feet, I should be able to think of this as, hey, this might be logarithmic. Because if you're multiplying your iterator by something greater than 1, or if you're dividing your range by something greater than 1, then you're looking at something that's logarithmic. So this then is logarithmic. On the bottom piece of code, lines 11 and 13, I can see those from that same 400 feet. I see those 2 pluses. I'm saying pretty much that's a +1. That's moving over one item at a time. That's probably looking at all the items. So this is linear in whatever the maximum value on that loop is. In this case, it looks like size, and size is probably my n, so that's an n loop inside an n loop. I multiply those together, and I got n squared. I look at all the rest of this junk. It's all constant time. I can walk away from that really super quick. Unfortunately, none of the problems on the exam are going to be quite this simple. But those techniques are there, and they're going to be that simple. You look for a loop. You see if there's division in there or multiplication in there. That's probably logarithmic. You look at those pluses or minuses. That means we're going one at a time, and that's probably going to be linear. You just have to figure out how broad the scope is on them, whether it's a linear on the whole thing or half of the thing. You figure out whatever that gives you, and then you can pull that together. All the rest of the stuff, you see constant time work, you just leave that out of the equation. You're just looking to interpret those things. So something as simple as this bottom piece of code, I would literally have that read and answered in 20 seconds if I was doing this. And hopefully you shouldn't be much longer than that. So the questions are going to have to be more complicated than that. But you still apply those techniques. You just look at each loop and right next to it, n, log n, and then you see who gets multiplied by whom, and then there's your answer, right? That's how you need to approach these things. The way that we get to complexity, of course, if we're not looping, is through recurrences, and those are a little bit more tricky. But in the end, we'll talk about that and try to simplify that as well. So here we see merge sort in line 1, turns around, calls merge sort in lines 5 and 6. So there we've got recursion right away. What's going on before we call merge sort again? Lines 2, 3, and 4, some comparisons, some return, a little bit of arithmetic there. All a constant amount of work, so constant in fact I might just ignore it altogether. It's totally unimportant. If I wanted to, I could put a C in my recurrence relation that represents all of lines 2, 3, and 4. Because no matter how far apart left and right are, lines 2, 3, and 4 take the same amount of work every single time. The epitome of constant. All right. Then, as I look at merge sort, I see, well, that's just a call to this. So if this in line 1 is T of n, how is line 5 written? It looks like line 5 has n over 2 items. because I've taken left to mid. That's half of them. I see the mid right there in line 4. So if 5 is t of n over 2 and 6 is the other t of n over 2, then I can see that this is 2 times t of n over 2. And then I just have to figure out what's going on with merge. If you get a question like this with some external function, we'll tell you maybe not what that function does. You don't care what that function does. What you care about is how that function behaves. So we'll absolutely say, well, whatever this merge thing is, it's linear in the total number of items. So then you can say, oh, okay, well this whole thing, t of n is equal to c, 2 through 4, plus t of n over 2, 5, plus t of n over 2, 6, plus c times n, or big theta n, because you told me whatever this magic function was, it was linear. So then as I go to put this all together, that's what it looks like. T of n is equal to 2 times t of n over 2 plus big theta of n. So now we've got our recurrence relation. Then it's just about solving for our overall complexity. So in this case, this one's a perfect candidate for using the master theorem. If I had something that was n minus 1 or minus 4 or something like that, then I would use the substitution method to get there. But in this case, what I'm going to do is use the master theorem. And the master theorem tells me that the leading coefficient of the t of n over something is a, that's a 2, and then the n over something, the something is b, so the divisor there also 2, and then the largest power, or the order of magnitude of the remainder of the stuff over there, that's just big theta of n, or c times n. That's my largest exponent there is 1. So I've got a equal to 2, b equal to 2, c equal to 1, and that sort of covers this master theorem setup there. And then if I plug those things in there, I see that this gives me the second case where a is equal to b to the c. That's just the middle one there, n to the c times log of n. So this is an n log n. So there we go. That's how we apply the master theorem, and we get the answer. All right, now this next set of questions, these are bad test questions, but this is not the test. This is the exam review. These are great review questions. They're great review questions because they're ambiguous. And so I ask you one of these questions, you can be like, well, it depends. I'll say, it depends on what? If you can answer the what it depends on, that's what's going to make you strong in the test. So down there at the bottom where it says also why, of course you're never going to get a why in a multiple choice quiz. So answering the why is important here. We see that we've got some structure stuff going on. So I'm talking about getting better at taking tests. So what I have is 3 bulleted questions, and then down at the bottom I've got 3 options. Right away my mind is going to go to, I probably will distribute them. So if I get to the end and maybe I've picked 2 of them, might be pushing me more towards the 3rd one. It doesn't say that they all have to be used, but that's how I'm going to think. So this is helping me sort of relax myself and say, hey, if I just get 1 of these right, it's probably going to help me with the other 2. If I can get 2 of these right, it's going to be even more help with the 3rd one. So that's kind of one way that I approach something like this. Now we'll see that it doesn't always hold, but it's a good place to start. The other thing I talked about too was how hard it is for us to write questions. It's really hard to write these questions because it's hard to give away so much information that we're very clear without giving away the answer. So right away as I look at these, look at those first 2. They're 2 lines each, 1 sentence each. Look at that 3rd one. It's 2 sentences there, twice as much text. That tells me there is all kind of information in that question. I just need to pull out of it what I can. So starting at the top, we're trying to find which one of these is the best container out of singly linked, doubly linked lists and vector. So the first one, what is the best container if it will be used primarily to locate objects within it using a binary search? I'm already at vector. Why? Because in order to use a binary search, I've got to have random access. I need to be able to jump to the middle of a section in constant time. If I can't get there in constant time, then what I've got is something that's linear. I'm all alone at the house here, and the front doorbell is ringing. 2 seconds pause, sorry. All right, I'm back. Sorry. They're working on my house, so I had to let them in. All right, there we go. All right, so what is the best container if it will be used primarily to locate? And I said I can't get there to the middle without random access. If I've got to use sequential access like a singly linked or doubly linked list forces me to, then I might as well just be doing the linear search. So I can say vector on number 1. Number 2, what is the best container if new objects will often be added immediately before specific existing objects? This one is a little fuzzy here, right? Right away, I can see that with a doubly linked list, I've always got access to that thing before me. So that's where I'm shading towards doubly right now. The depends part is, if I'm trying to put it in front of a vector, I know I've always got to move things if I put something before something in a vector. So vector is kind of pushing its way out. Doubly linked list is pushing its way up. Why not a singly linked list? There's where it depends. If I give you a pointer to the thing I want to insert in front of, with a singly linked list, you just have to start at the beginning and next, next, next to get there. So that's not great. But if I say I want you to insert before something, go ahead and start at the beginning, then you still have to take that next thing to get over there, but your insertion can be done in constant time. So it depends here. However, the one that answers this question in all the cases, the best, is the doubly linked list. Because no matter what, if I'm pointing at it already, I can get it done in constant time. Now, look at the last one here. What is the best container if you must store a small number of very large objects? Right away, we have more information than those previous 2 questions gave us. They were just like locate object, new object. This one says we've got a small number of objects, and it says that the size of these objects is very large. So the question asker is pushing me towards something, because now they're saying size matters, quantity matters. Why is that? Continuing. Memory is scarce, and the most important consideration is to store as many of these objects as possible in the available space. So when memory is scarce, now I'm starting to think, well, I don't want to spend too much overhead. Where do I get overhead? I definitely get overhead from doubly linked lists, because that's got, 16 extra bytes, so a pointer here, pointer there for every object. So doubly linked list is already sort of settling its way down. So you could say, well, vector could be it, but I also, if I've got really large objects, I might not be able to declare enough of them contiguously to make it a vector. So having a pointer to jump between them might be nice. So this is not a great question, just because it's a little hazy here at the end. But it's the answering of those questions where it's like, well, it depends. Well, it depends. If I can't move things around, then I would probably use a singly linked list. If I knew ahead of time how many there were going to be, I could put them all in one block, then it might be vector. So it's those depends answers that are really good in making sure that you're ready for questions that you're not looking for, that you haven't seen before when you come into the exam. So there's my answers there. Vector, doubly linked list, singly linked list. This one flips it around. Now we're looking at worst. Worst, worst, worst. Same 3 options, singly, doubly, and vector. What's the worst container if you must store a large number of 1-byte items and memory is the scarcest resource? Once again, when we're talking about using memory as a scarce resource here, I'm looking at overhead, and the doubly linked list has overhead of 2 pointers per data item. And those are 8-byte pointers on a 64-bit machine, so 8 bytes this way, 8 bytes that way, that's 16 bytes. If I got 1 byte of data in the middle, then 1/17 of my space is data, and 16/17 of it is all eaten up in overhead. And if I got to store a whole bunch of them, that's not the way to get it done. So I can say the worst right off the bat, doubly linked list here for sure. Singly linked list has half that problem. I've got half the pointers, so I still got overhead there. Vector's probably the best there because, I can keep, a bunch of 1-byte items contiguously, and then my overhead there is just 3 pointers. 1 pointer at the beginning, 1 pointer at the end, and 1 pointer at the end of data, and there you go. So that's my best memory overhead there. So the best option of the worst. So worst is doubly, probably best is vector there in the first one. What's the worst container if you will frequently insert new items anywhere within the structure? So there's a good argument for vector not being fun. Anytime you have to insert something in a vector, you've got to move everything else after it backwards. This could also be the singly linked list, depending on how you're going to get the value. If you're saying, I want you to insert before this item in the singly linked list, it's just as bad as a linear search to get from the beginning to next, and put it before this. It's a constant amount of work once I get there, but it's a linear amount of work to find the place. So the worst one there could be vector. It could be singly linked list. Now I'm at a quandary here because I don't have a solid answer for number 2, and I've ruled out 1.5 items by the time I'm getting to number 3. What's the worst container if you'll frequently insert new items at the beginning of the structure? Okay, there's no getting around this one. It's always vector. I know that it's bad here because if I've got the beginning, I can easily insert into any sort of linked list very simply at the beginning if I know it's the beginning. I don't have to know anything else. So the worst there is definitely vector, and the other two are equally as best there. So here's your answer. As I mentioned, you don't always get the full distribution there. So the worst container could be the vector there. It could also be the singly linked list. As I mentioned, it kind of depends on how you're being passed the problem. If you're being passed it by a pointer to the object you want to insert in front of, singly linked list is just as bad as a vector in this case. All right. Stacks and queues. This one's great. Implement a queue using 2 stacks and 8 lines of code to get it done. We're going to show you some stuff here. So anytime you've got something like this, you want to take from it what you can, right? And I talked about the code, the questions being long, that's giving you information. Here there's code that's giving us information. You see that I've got 2 stacks, trying to push things in there and get queue behavior. And what does queue behavior does? You know, 1 goes in, 1 comes out. 1, 2, 3 go in, 1, 2, 3 come out in that order. Whereas if I've got a stack, if I push 1, 2, 3 in, I'm going to get 3, 2, 1 out. Stacks always reverse things. And so I'm trying to implement a queue here with a stack that reverses things, but I want things to be in forward order. And what comes to mind right away is the enemy of my enemy is my friend, right? If I reverse things and then reverse that, I've got them the way that I wanted them, right? And so here we can get that out of this. The code is given to us. In line 2 there, we've got 2 stacks declared internally. Line 4 has got 4 and 5 have push implemented for us. So push is always pushing things into stack 1. And then I've got pop in front, and I haven't shown you front because front basically tells you pop as well. So you don't get all of the things. You have to figure this one out. Take a few seconds here and see if you can figure this one out. And then there's bonus points if you can tell me what the complexity of the pop that you wrote is. All right? You think? I'll drink. All right, so I gave you the prime insight on this one. The enemy of my enemy is my friend. If I reverse these things and then I reverse them again, I get exactly what I want. And I've got 2 stacks, 1 for adding things and 1 for reversing and removing things. How about that? So I'll push into stack 1 and I'll pop from stack 2. And anytime that I need to get stuff into stack 2, I'll just pop it out of stack 1 and put it into stack 2, because then it will be in reverse order and it will come out of stack 2 in a reversed reverse order or the original order. So here's what it looks like. We see at the very end just what I suspected. S1 is my push stack, and line 18 says S2 is my pop stack. That's how I get rid of stuff, by popping S2. Inside the rest of this, I've got the trick, right? The trick is, if S2 is empty, then obviously I can't pop from it. I need to go get everything I can from S1 and move it into S2. So if the second stack is empty, I'll take everything from the first stack and put it in the second, because now they will all be in reverse order or my original order. So think about how this might work. If I push 1, 2, 3, 4, 5. Okay, I expect to get out 1, 2, 3, 4, 5. I expect to pop them in that order. So 1, 2, 3, 4, 5 go in, and then someone asks for a pop. If I then flip them over, right? Here's 1, 2, 3, 4, 5. They go in like this. And if I put them into stack 2, then they can come out 1, 2, 3, 4, 5 like that. No problem. So that's what this does here. And what about the fact that I've left everything over in stack 2? Is that a problem? Is that a problem? Well, let's try it. Right? Let's push 5, pop 1, and then push 6. And see if I 1 through 5, sorry. Let's push 1 through 5, pop 1, which should be 1 because that was the first one in, and then push 6 and see if I've got what I want. So I take 1 through 5, I put them in, then I go to pop 1, so I have to invert them. Now I can pull 1 off, and then I put 6 in over here. What happens? If I get another push, I'll put 7 in on top of 6. If I got another pop, I'll take 2, then 3, then 4, then 5 popped. Now if I go to pop again, I still have 6 and 7 in the container, but since stack 2 is empty, I'll put 7 and 6 in there, and then I can pop out 6 and pop out 7. So it turns out that when I start popping, I don't have to return things back to some intermediate state. I don't have to put them back into S1 just to allow me to add more items to stack 1. Just remember that I only push into stack 1 and only pop from stack 2. Those things allow that separation to be maintained. Sort of like a temporary list that's always held in stack 1, waiting to be sort of moved into in a chunk over into stack 2, and then they can be popped out in order from stack 2. So that's how that works. Then the bonus question here was, what was the complexity of that? Well, you should think one of those pops is crazy expensive. I just pushed 50 items in there, and now I want to pop one. I got to move 50 items to just get that one item out. But once I've done that, the other 49 come out in constant time. Boom, 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 boom. So one of them is really expensive. The rest of them are really cheap. Spiky, that's what we called it in lecture. It's a spiky profile. So this then, if I do the math on it, right? Constant time going in. Everyone is always just a constant time push. So it's constant time going in. But as I go to start pulling them out, I see that, say I push 50 of them in, my first pop makes me have to move 50 items. Boom. And pull one out. So there's like 51 operations. Now I've got 49 items that are ready to go out in constant time. So those 49 items come out at 1 step each, and so I've got a total of 100 steps. 50 to invert and 1 to pop out, and then 49 pop outs. And that got me my 59 items back, my 50 items back. So if I add all those steps up, 50 plus 1 plus 49, there's 200 steps to get all 50 of those items out. If I divide that by the 50 items I got, I say 200? This is 100. We got to add and stop talking. 50 to invert. First one comes out in 1, the next 49 also come out in 1. That's 100 steps to get me 50 items. So those 100 steps, the number of steps per item is 100 steps divided by 50 items. It looks like on average it's about 2 steps per item. Even though I know that one of them cost me 51 and the vast majority of them cost me 1, that's still a constant. That amortizes down to a constant because as I take those 100 steps, divide by the 50 items, or maybe I double that. So now I've got 100 items in the stack. It takes me 101 to get the first item out and 99 for the rest of them. But now I get to divide by 100. So no matter how many items I add, I'm still dividing by something that looks like half of them. And I still end up with a 2 here. So with 50 items, it's going to be looking like a 2. With 1,000 items, it's going to be looking like a 2. So this then is a very good example of amortized constant. Kudos to those who got that, and even more kudos to those of you now who have a better understanding of amortized constant. Because this is perfect. This is just like This is just like a pushback. One of those is very expensive because we got to copy things to a new location, but then the rest are cheap. Here, one of these pops is very expensive, but the rest of them are cheap, right? This is an amortization schedule, right? When you get a mortgage, I don't know if you've looked into this, when you get a mortgage, you pay interest, and every payment is part interest and every payment is part principal, and you never pay the same amount twice. Very first payment, you pay more interest than the second payment, you pay more interest than the third payment, you pay more interest than the fourth payment. You get down to the very last payment, you're paying almost no interest whatsoever, and it's mostly just principal that's being paid off. But that's an amortization, so you can say that I've got an average cost that I pay every month. It's just that I'm paying off the interest in a different way. So this is what amortization is all about. You have to take the entire cycle. In this case, it's my one expensive pop for many cheap pops. I take all of that cycle and divide it by the total number of pops, and that's how I can get my cost there. Amortized constant. Excellent. On to sorting. Unless otherwise stated, we're always going to use the best, most adaptive version of a sort that we've developed. So here's another sort of gang properties question. Which sort is the best in these circumstances? So I didn't even give you a list of the sorts. You can remember what they are. Selection, insertion, bubble, quick, merge, heap, whatever. All right, 5 options. An array that's almost already sorted, a very small array, a medium-sized array. Look at that next one, a large array. That's kind of in keeping with the other questions. It's just size, array word. But there's also about as big as main memory. That's a perfect example of the question asker giving you information because they want to be clear here. So about as big as main memory should point me to something, and we'll see what that points me to in a minute. And then a very large tape drive. I realize most of you were all born after the destruction of all tape drives, but it's an old school mass bulk storage device that you'd put on a slow tapes. They were very slow, but they held a lot and they were hard to get information off of, but it was always all there. So there we go. Then the bottom question says you're using quicksort on a very large input and it's taking longer than normal. What has happened? So those are the questions. Let's get after this array that is already almost sorted. Well, if you remember some of those properties, we said that because of the low number of inversions, when something is already almost sorted, then it looks like insertion sort and bubble sort happen in almost linear time. So, an array that's already almost sorted, I'm going with insertion or bubble. A very small array. Yeah, we're definitely going with insertion. That's the fastest there is on a small one. There's some other depends on this one, but a really good answer there is definitely insertion sort. A medium-sized array. That's gotten away from just about everything else now. It's not already almost sorted. It's not very small. We're thinking general information, general size. Generally, the fastest thing we can do is quick sort. So quick sort comes to mind here with this medium-sized array because I don't want to do anything elementary here because once we're in a medium size, I know that I'm going to be dealing with n squared if I'm using those elementary sorts. I want something that's n log n. Medium-sized array then, we're looking at heap sort, merge sort, quick sort. The fastest of those is quick sort. So, large array, about as big as main memory. Now, what's going on there? It means I can get it all in there. It's an internal sort in the sense that it's all loaded. But I don't have a lot of extra space. Not enough space to make a copy. So, very large means there's no way n squared is happening. That rules out selection, insertion, bubble. About as big as main memory means I can't copy it, so that rules out merge sort. Merge sort has to have a full copy. So now we're stuck with just quick sort or heap sort. Which should we use? Well, if it's about as big as main memory, that's actually large. That's a lot. If you think about a 16 gigs of RAM machine, that's a lot of data. How many stack frames am I going to have to go into to make that happen? So maybe stack frames is not the thing here. What if I stick with heap sort then? Because it still can be done in actually a constant amount of space in the algorithm and in the implementation, whereas the quicksort algorithm is constant amount of space in the algorithm, but the implementation has got my stack frames involved. So I would say with a very large array here, that's pushing me towards a heap sort answer. A very large tape drive, of course, is what merge sort was invented for. If you go watch some old 70s movies with computers in it, you'll see these things that look like refrigerators that have big reels of tape on them. They're spinning, and this is where all the suspense comes in. And it's one big refrigerator spinning tape with source to another big refrigerator spinning tape with source to one big refrigerator that's reading and spinning tape to put the destination in there. So that's what that's for. That's merge sort. So here we are. Insertion sort or maybe bubble, that's what we thought in the first one. I said selection sort for very small because that was great, but there's also selection sort if I've got large data, because I know that moving data around can be expensive. And even if I've got a small amount of moves to do, if they're big objects, it's going to take a lot of time. So selection sort on a very small array with very large items would actually be the thing there, because when selection sort has big data items and small keys, it too looks linear in the amount of things that need to be done, because you're doing a linear amount of data moves, even though you're doing a quadratic amount of comparisons. If those comparisons are much faster than your data moves, then it still looks like it's a linear sort. So very small array gets two options there. Quick sort on medium size array, maybe heap sort, depending. But the primary answer there is, again, quick sort. And then, of course, here on the large array, I said heap sort would probably be your goal there. And lastly, the merge sort is the tape drive sort. This one was pretty straightforward. If you're on a quick sort with a large input and it's taking longer than normal, what happened? You just got a bunch of bad pivots in there. So we're starting to go towards our n squared worst case. All right, this is another good one. Binary heaps. Real super straightforward. Draw the underlying array for the heap. This is a really ambiguous test review question. If I'm going to ask you this question, I would say, you know, this has to be 0 indexed, or this has to be 1 indexed, or here's the boxes, put things where they actually belong there, right? That's what's going to happen in a real exam. But for your purposes during study time, this is good enough. Draw the underlying array for this heap. So we know that we've got 9 items here. I'm going to put 81 at the beginning, the farthest left, the 0 index or the 1 index, the first item. Then its 2 children follow that, 18 and 41. Then the 2 children of 18, 9 and 7 follow 14. And then 1 and 5, the 2 children of 14 follow 7, and 2 and 4 follow 9. So to read that in order would just be 81, 18, 14, 9, 7, 1, 5, 2, 4. Those are my 9 items. I put them in memory like that. There we go. Dummy element if you want one. Like I said, this is not a test question. This is a review question. Push the value 47, and the extra hint of use fix up. Of course, you've got to use fix up. So if I push 47 in there, where does it end up for starters? For starters, we know that there's going to be a third element on the 4th row. So it's going to be the farthest left one. So that would be 7's left child is where 47 goes in. Then I have to fix 47 up. I look at 47 versus its parent 7. I'm doing a swap. Okay, 7 go down, 47 go up. Now I can look at 47 versus its parent, because in a fix up, you're going to take the item that you just inserted and either fix it all the way up to the root or fix it up until it stops making things swap. So as it's in that 3rd row there, I look at its parent 18, 47 bigger than 18. I do the 47, 18 swap, 18 go down, 47 go up. And now 47 is the left child of 81, and it's where it belongs. All right. Draw the resulting tree and array. That's all practice stuff. Now, let's talk more about how to win at exams. Binary heaps, hopefully, logical and physical, are pretty tame stuff for you right now. Hopefully this is not too hard. When you look at this, you're like, okay, I get this. It's great. Doesn't matter. There's still going to be a question or two about this on the exam. So even if this looks very simple to you, you still have to pass the test. You still have to answer the question properly. So here is another great study technique for prepping for an exam. Think about, what might I ask you? Because you look at this, you're like, oh, that's easy. I got this. How am I going to ask you to prove that you got this? Think about what kind of test question might be written to show that you know how to do this. And what are we doing? We're writing a multiple choice question here. So how am I going to get you to draw an underlying heap in a multiple choice question? I guess the obvious way is I could give you the answer in a collection of pictures and say, pick which one of these pictures is the one. That's probably the easiest way I'm going to give it to you though, right? Another way might be like, okay, well, here's the underlying heap. I show you this nice logical version. What you're going to do is push 47 and then tell me what is the right child of 47. Is it 9? Is it 18? Is it 7? Is it 1 or is it 5? There you go. That's 5 multiple choices. Like, if you know how to do this, you would answer, oh, it's definitely 18. That's the right child of 47. So there's a way to write a test question. And these test questions aren't written by evil geniuses, right? Well, I guess they're written by the staff. So some of the staff are definitely evil geniuses. But we love them just the same. But the staff members that we have on this, about 1/3 of them every new year are new IAs. They were somebody who just took this class last semester. And they end up writing a portion of this exam. I say this to put your mind at ease, to let you know that, 25 to 33% of this exam was written by someone who's got one more semester of experience at 281 than you do. So they can think of these questions, then you can think of these questions. There's my challenge. If you're going to put together a study group tonight, everybody jump a Discord channel and say, I'm going to contribute a multiple choice question. If 100 of you write 2 multiple choice questions, and now we've all got 200 more questions to practice on, by we, I mean you, of course, that's going to be helpful because this is somebody else thinking of how can I show whether I know this? How can I test to see if somebody else knows this? That's my job. It's not that hard a job though. I try to teach you things, then I try to figure out what you've learned. So if you work on this yourself, you can say, I'm not going to really draw the resulting tree or write, I take that back. On one particular short answer question in a previous exam, we did have somebody draw a tree and then we graded trees. We don't do that very often though. It's much more likely that we're like, okay, well, after you do this work, here's a multiple choice question that lets you describe how this works or how it should look when it's done. So that's what you should do as you take your studying forward on this and any other exam. When somebody's given you a topic, sure, it might be easy. But what they might ask you might not be that easy. You might understand it very well, but if you don't think like what kind of question is coming before me, like that's just like going out saying, I don't know, I think that team plays defense. Oh, you didn't realize that they're known for their 2-3 zone and they're going to hit you hard with the 2-3 zone? That's you going in planning to fail. Right? So if you can come up with questions or think of how questions might be asked of you, you're much better prepared to figuring out how you're going to score on this exam. So I've already run through this one. I did the blue slide and I didn't have my tablet set up today. But like I said, this one is not that difficult. You would push 47 in at the very end, right? That would be index 10, right? And then if you look for index 10's parent in the physical sense, you just take that index 10 divided by 2, integer division gives me 5, and I know that at index 5, the 7 would be 47's parent. That's where my swap happens. Then I keep moving up integer division on 5 gives me 2, so I know that then 47's parent, once it was swapped to the 5 location, would be the 2 location, or 18, and so on. So there you can go play with this one. If you haven't got this already drawn up or written up in the array format, you should be able to figure it out pretty easily. All right, PQs. We certainly bashed the heck out of PQs in P2, didn't we? Right? We looked at unordered, we looked at sorted, we looked at heap-based stuff, we looked at binary heap, we looked at pairing heap. Luckily, no P heap on the exam. So let's just look at these 4 operations: create, range constructor, push, pop, and top. You should know them. These are literally in your files already. You should have that. An unordered array, to create it, we just put it all in there, linear time to copy it over there, and we're done. A sorted array, we need to copy it over there in linear time and do an n log n sort on it, so that's an n log n. In a binary heap, I've got to copy it over in linear time and heapify, which is also linear time. So there's that front row. In push, for the unordered array, I can put it anywhere, constant time. In sorted, I have to put it in order, which means moving some things out of the way, linear time. In a binary heap, I'm going to put it at the bottom of the heap and fix it up, worst case, log n time. Top, the great thing about the ordered sorted arrays and the binary heap is we know where the top item is at all times. So both of those are constant time. In the unordered array, I'm going to have to do a linear search, so that's a big O of n there. And then lastly, in pop, in the unordered array, if I knew where it was because I previously did a top, I can pop it in constant time. If I didn't know where it was, it might take me linear time. The other two are straightforward. In a sorted array, it's always at the back. I can remove it in constant time. In a binary heap, I've got to break the heap by removing the top element and then doing a swap and fixing things down. So that's going to be a logarithmic joint right there. So there's those things. Like I said, this is a decent chart to have on your exam cheat sheet just so that you can look something up. But I think the time that you would take your focus off of the thing to go look that up, I think you probably already got that up here. So use that when you need to. But if writing this stuff down calms you, calm yourself. Don't use it, but be calm when you get there. Whatever works for you, make it work. All right? Last one here. This is strings and sequences. As I mentioned, there is one question. I think there's the pool that has the strings and sequences question in it. There's only one question on the exam. So you'll only see one of them. There aren't too many. We just covered it. It was our last topic. Sometimes we don't even put strings and sequences in till the final because it's so close to the midterm. But with the break this time, you've got time to deal with it now. We did this about, 8 days ago by the time we get to the exam. And even if they waited for my lecture, it didn't come out till the Thursday after that. It's still 6 days before the exam. So pretty decent. What is a string fingerprint? That's the way that we convert a string to some integer. Then we can use that integer to compare strings. And what that does is it makes it easy to find negatives, and it has the ability to sometimes show a false positive. Meaning, if two strings have their fingerprints and the fingerprints are different, I know for a fact that those are two different strings. Right away, without having to look at any characters in the string, I can just compare the fingerprints. If the fingerprints are the same, then there's a chance of false positive, meaning that these two strings are different, but have the same fingerprint. It's very rare, but it's a thing that you do have to check for. So you go back, check for it, and then you're good there. Turns out that most of the time, when the fingerprints are the same but the strings are different, they're actually sort of wildly different strings, and so it's pretty quick to figure out that they are not the same thing. So that's what it's all about. You don't need to know how to compute a fingerprint. You won't be asked to compute a fingerprint on the exam. You will be asked, if fingerprints are the topic, to use one, to know how to use one, or what the importance, basically what I just said. The stuff I just said, that's your answer. Supply it. All right? So, this is what's coming at you. It's happening tomorrow. It's not going to be the end of the world. Go into it well prepped. Go into it well rested, well fed. Get yourself some quiet. Make a plan. Run the plan. Score points. Put them on the board. And then go out and do whatever it is that you have to do to celebrate the fact that the midterm is done. And we're going to start again the next day and get cranking on the second half. All right, we'll answer some more questions in chat here, but that's me signing it off here. All right.